everybody. Welcome to West Virginia. Life is a circus. So let's just circus our way into Joke of the Day. You know, what music do ghosts listen to? Well, of course, it's soul music. Anyways, let's just soul our way or music our way and let's just dance our way into equations with rational expressions. I just botched that terribly, but that's okay. Equations with rational exponents. So recall that rational means not rational dude, but rational means can be written as a fraction. So what's going to happen here is we're going to have equations where we're going to have fractions in the exponents. They're going to look kind of like this right here. Fractions in the exponents. Now recall that when we get our solutions, we always wanted x to the first power. We didn't want x with these crazy exponents like even a 2 or any kind of a fraction. We want x to the first power. So in order to get x to the first power, we have to get rid of that fraction, that exponent. So we have to kind of recall a couple of things. One of the things that we need to recall is that whenever we take a power and we raise it to a power, what do we do with those exponents? Go back to those laws of exponents. When you take a power and raise it to a power, then you're going to multiply those exponents. And remember, when those sit right beside that parentheses, that indicates multiplication. So I'm going to take this power, I'm going to raise it to that power, and whenever I multiply fractions, what happens? Exactly. Gang symbol, here it is again. Whenever you multiply fractions, you cancel on those diagonals, you cancel up and down, and then you shoot straight across. So what's going to happen here is, I'm going to cancel on these diagonals, and you'll notice that the m's will cancel, the n's will cancel, and you are just left with a 1. So what happens here is, whenever I have a rational exponent, or an equation with a rational exponent, I'm going to take this side, and I'm going to raise it to the reciprocal power, raise both sides to that reciprocal power, because these will cancel. Whoops, I didn't do reciprocal power, I did exactly that power. Reciprocal power, so that when I multiply, I'm going to cancel those diagonals. The m's will cancel, the n's will cancel, and I will get my x to the first power. But what I do on one side of the equal sign, I have to do on the other side of the equal sign. So I will raise this to the n over m power as well. But we need to recall something else, this idea of what does that fractional exponent mean? Well, remember, when I have a fraction in the exponent, the denominator means root. So this is going to be the nth root of a. So I could either write it as, I'm going to take, and I wrote this completely wrong. Wait just a minute here. This is exactly the same thing. Let me step back a second. It would either mean I'm going to take my a and raise it to the n power, and then take the nth root of that, or I can take the nth root of a and raise that to the n power. They all are going to get the very same result, and the point is denominator means root. So when I do that k to the n over m power, I'm going to take the mth root of k, and then I'm going to take that number and I'm going to multiply it by itself that many times. Because I'm doing a root though, because I'm doing root, then I have to consider the plus minus if necessary. So, I'm sure that this is all kind of feeling a little weird, so let's take a look at our first example. We'll refer back to these steps here in just a minute. But take a look at the first example. I have 3 times w to the 4/7 power minus a 48, and so recall that I want w to the first power. I don't want w to the 4/7 power, w to the first power. So I know, okay, that means if I raise this to the reciprocal power, I'm going to multiply those exponents. But recall that when I raise it to that reciprocal power, I can't just raise this term to the reciprocal power. Even more so, I can't just go in here and go like this and raise just that factor to the reciprocal power. Whatever I do to the side. So when I take this side and I raise the side to that reciprocal power, I have got a big, huge problem on my hands because I don't want to take the 7/4 power of a 48 and a 33. This is just complicated. So maybe what would be best would be to get that w to the 4/7 completely by itself, so that once I get it completely by itself, then I can go ahead and raise it to the reciprocal power. And I'm I'm going to cancel in those diagonals, and sure enough, the exponents will completely cancel out, and I'll get that w to the first power. So my first step, let's go back to those steps again. My first step is actually going to be to isolate that term that has the rational exponent. Now, it does say expression. We'll take a look at that in the second example. But the idea is get the term that has the rational exponent completely by itself. Once it's by itself, then you can raise both sides to that reciprocal power. And be very careful about that plus minus. So let's go back and take a look at that. I want to get that w to the 4/7 completely by itself, which means I'm first going to add that 48 to both sides. And then I'm going to divide both sides by 3. And when I divide by 3, I will get that w to the 4/7 completely by itself. And then 48 divided by 3 is a 16. So that now, when I raise this side to the 7/4 power, I'm as well going to raise this side to the 7/4 power. So this is where I said, okay, we need to remember that denominator means root. Yes, over here I do get w to the first power, which is fantastic because that's what I wanted. But now I need to evaluate this side. Denominator means root, so that means 4th root of 16. Once I get the 4th root of 16, I'm going to raise that to the 7th power. Now, 4th root of 16 means what number would I multiply by itself 4 times to create a 16? Well, that would be a 2 because 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. However, what about a negative 2? Because negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And negative 8 times negative 2 is positive 16. So this is where I said I need to be very careful and I need to think about that plus minus. In other words, if my root over here is going to be even, in other words, if the m is even, then I need to insert that plus minus. If that root is odd, then I don't want to insert the plus minus because it won't work, which we'll see in the next example. So let's go back to this. So what I'm going to do is I'm going to take the 4th root of 16, which we have just figured out is a plus minus 2. Now I'm going to take my positive and my negative 2, I'm going to raise it to the 7th power. So 2 to the 7th would be 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. So I'm going to get a 128. Now recall that when I do negative, an odd number of negatives results in negative. So therefore, I'm not only going to get a positive 128, but I'm also going to get a negative 128. But now remember, I do need to check for those extraneous roots because of this idea of taking that square root. So I need to check and see, will they both work? Now, it's very easy to check them both at the same time. So what I'm going to do is take my positive negative 128, put them both in here at the same time. If that's confusing, you can certainly check them individually. But watch how easy it is to check them together. So when I put my positive negative 128 in there, notice I'm raising it to the 4/7 power. I'm going to follow order of operations, which says do parentheses first. Inside this parentheses is just one single number, so I'm not worried about that. I'm going to head on to exponents. So 4/7 power means I'm going to take the 7th root of the 128. So what number would I multiply by itself 7 times to create a 128? Well, that's a 2, because that's how I got a 128. Now, if I take the 7th root of positive 128, I get a positive 2. But if I get the 7th root of a negative 128, I get a negative 2. Now I'm going to raise that to the 4th power. So now 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. Now if I do positive 2 to the 4th, I get a positive 16. But interestingly, a negative 2 to the 4th, I have an even number of negatives, makes my answer positive. So now continuing on with this order of operations, 3 times 16 is 48 because I do my multiplication next. And finally I will subtract and I will get 0 equals 0. So yes, in fact, it does work. It's not an extraneous root. It is a solution that works, and both of them work. So once again, the idea is I need to isolate what has that rational exponent so that I can raise it to the reciprocal power. Now, as you look at this one, very strange, but remember, this entire parentheses is being raised to the 2/3 power. Sometimes I put my hand over the parentheses so I don't confuse myself. It's parentheses to the 2/3 power. So, actually, it has been isolated. This is where I said in the steps that we would isolate the term or expression that has the rational exponent. Because here we have within that parentheses an expression that is being raised to that rational exponent. So it is isolated. And I am ready now to go ahead and just raise it to the reciprocal power. Now the reciprocal of 2/3 will be 3/2. And what I do on one side, I have to do on the other side. So remember that when I cancel those diagonals, because I'm multiplying fractions, the 2's will cancel, the 3's will cancel. I will simply be left with a 3x plus 5. And on this side, I'm ready to evaluate, remembering that denominator means root. So this is going to be second root, which is square root of 4. And once I take that square root of 4, I'm going to raise it to the 3rd power. So now, square root of 4 is 2. And remember, I took the square root here. It wasn't already on the page, so this doesn't indicate positive or principal square root. I have to consider all those roots. I have to consider the plus minus now. Because a positive 2 times a positive 2 will give me a 4. A negative 2 times a negative 2 will also give me a 4. And remember, I need to consider that plus minus because that square root was not already on the page. It was not already on this side. I took the root over here. Same thing over here. I took the root over here. And because I took the root, I need to consider that plus minus. So now, when I take that positive or negative 2 and raise it to the 3rd power, positive 2 to the 3rd will be 2 times 2 is 4 times 2 is 8, and it'll be a positive 8. But negative 2 times negative 2 is positive 4 times a negative 2 is a negative 8. So I need to be very careful about that plus minus. So my 3x plus 5 could be an 8. 3x plus 5 could be an 8. Or that 3x plus 5 could be a negative 8. Now if 3x plus 5 is 8, I'm going to subtract that 5. And then I'm going to divide by 3. And my x will be a 1. Here, if it's a negative 8, I will subtract my 5 and get a negative 13. And then I will divide by 3 and I'll get a negative 13 over 3. But remember, I need to check for those extraneous roots. So when I go to check, and I can't check both of these at the same time because this is not an issue of a plus minus. So when I go to check the 1 and I put the 1 in here, that's going to be 3 times 1 plus 5 in the parentheses. I'm going to raise that to the 2/3 power. And once I do that, I better get a 4. Now inside the parentheses, because remember, order of operations says do inside the parentheses first. Inside I've got multiplication and addition. I will do the multiplication first. 3 plus 5 will give me 8. And now I'm going to take that 8 and raise it to the 2/3 power. Which means I'm going to do cube root of 8. And once I get that, I'm going to raise it to the 2nd power. Now, cube root of 8 is 2 because 2 times 2 is 4 times 2 is 8. Now I'm going to take my 2 and square it. 2 squared gives me 4. So yes, that does work. 1 is not an extraneous solution. Now, let's go and let's check our x equals negative 13 over 3. So when I plug that right in here, that'll be 3 times negative 13 over 3. And everybody has a heart attack when those fractions show up. But stay calm because they typically work themselves out. And you're going to see it work itself out here beautifully. So go inside that parentheses first. Inside, I'm going to do that multiplication. And I'm going to cancel those diagonals. And I'm going to be left with a negative 13 plus 5. that I'm going to raise to the 2/3 power. Now, negative 13 plus 5 is a negative 8. I'm going to take my negative 8 and raise it to the 2/3. And that means cube root of negative 8, which means what would I multiply by itself 3 times to get a negative 8? Well, negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is a negative 8. So the cube root of negative 8 is negative 2. Now I'm going to take that negative 2 and square it. Negative 2 times negative 2 is a positive 4. So sure enough, it works. So both of these are solutions. But like I said, very important that you check for those extraneous roots, because sometimes when you plug them in, they will cause problems because you've got roots in there in your equation. So whenever you have equations with rational exponents, the point is you need to isolate that term or expression that has that rational exponent. Once you do that, you're going to raise both sides to that reciprocal power, because what you do on one side, you got to do on the other. And the goal is you want x to the first power, not x to some fractional power. So raise it to the reciprocal power. But be very careful about that plus minus. And if you're taking that root down there, you're definitely going to insert that plus minus. Check all your solutions for extraneous roots. Now, what I've looked at here is the simpler cases where you've got some fairly easy equations to deal with. That first example, we just slid a constant over and divided. The second example, we just had one expression that was to that rational exponent. There are more complicated cases, but we're going to keep it kind of simple in this video. So I hope it helped. Have a fantastic day.